Hey everyone, welcome back to the Foundry by Forge College. I am so excited to jump into today's explainer, preparing compiled contracts for deployment and managing builds. Now, if you hung out with us during our last lesson on applying parallel patterns, Project Increment, you know we've been getting our hands dirty compiling smart contracts as part of our broader look at Hardhat fundamentals within the Ethereum dev stacks and frameworks track. We've watched that raw source code transform into compiled outputs. But today we're taking a massive step forward. We're going to talk about managing those builds so they don't devolve into a tangled, undeployable mess. Think about it like this. Your Solidity source code, well, that's your creative brainstorm. Today, we're taking those big ideas, drafting up the official factory blueprints, and getting them so perfectly organized that your automated deployment lines can actually run without a hitch. So, let's get organized. All right, here's our roadmap for breaking this whole abstract software build system down into simple mechanical parts. First, we'll trace the path from compilation to deployment. Second, we're going to crack open a contract artifact and see exactly what's inside. Third, we'll tackle the infamous reproducibility problem. Fourth, we'll weigh out 3 distinct storage strategies. And finally, number 5, we're going to learn how to build the absolute perfect manifest. So let's dive right into section 1, from compilation to deployment. We are moving off the drawing board and stepping right onto the factory floor. Here's the thing you really need to understand right out of the gate. Compiling a smart contract, it's not just some magic trick where you mash your code into a bunch of unreadable bytecode. No, it's a highly structured process. When you hit compile, you aren't just spitting out data for the EVM. You're actually generating these beautifully structured records. Your Solidity code is the grand idea for sure, but the compiled output, what we call the artifact, that's your physical blueprint. It's literally the bridge tying your application binary interface, your compiler metadata, and your bytecode straight back to your original source code. Honestly, without this blueprint, your deployment scripts would have absolutely zero clue what to do with the code you just spent all that time writing. Moving right along to section 2, inside the contract artifact, reading the engineering blueprints. Let's actually pop the hood here and see what your Hardhat environment is churning out. In the Hardhat world, an artifact is definitely not just some random blob of data. It is a highly structured JSON record, and you'll usually find it just sitting right there in your artifact/contracts directory. Its whole job is to connect your compiled outputs back to the source code and, this is crucial, to the exact compiler environment that originally produced them. You really want to think of this JSON file as the canonical, machine-readable description of your contract. It's the ultimate source of truth. Your deployment scripts, your test harnesses, any off-chain tooling you use, they're all going to be constantly referring back to this exact file. Okay, let's break down the anatomy of this JSON record. What's actually inside? First up, you've got the ABI. This is your contract interface formatted as a JSON array, and it's absolutely required for libraries like ethers.js, for example, to encode and decode any off-chain calls. Next up is the bytecode. This is your creation time EVM data. It's the heavy payload that gets pushed when you actually deploy, and you'll use it later for contract verification. But wait, right below that, we have the deployed bytecode. Now, this is slightly different. This is the runtime code that actually lives at the contract address after it's deployed. It's exactly what you need to look at when you're calculating gas costs or messing with proxy patterns. And finally, we have the metadata. This is just a JSON string of your exact compiler settings. And let me tell you, this little field right here, this is the secret sauce for reproducible builds. Which brings us perfectly to section 3, the reproducibility problem. Subtitle, but it works perfectly on my machine. Oh yeah, the classic developer battle cry. Let's talk about the absolute chaos of local development versus the strict, unforgiving rules of continuous integration. So let me ask you a question. Why does build reproducibility actually matter? I mean, why can't we just casually compile things on our laptops, shrug our shoulders, and push the whole thing straight to the blockchain? Well, here's why. In your local environment, you're probably iterating pretty quickly, right? But if your compiler settings are unpinned, say you're just using a slightly different Solidity version than the rest of your team, you end up creating random bytecode fingerprints. The source code might look exactly the same to you, but the output absolutely isn't. Now, fast forward to your continuous integration or CI pipeline. If CI runs a compilation using different settings than your laptop, that bytecode fingerprint changes again. And when you finally go to deploy and verify your contract on a block explorer, it's going to fail. It's going to cause massive, massive headaches. And that right there is exactly why CI pipelines rely on pinned compiler settings. They guarantee exact, verifiable bytecode fingerprints every single time without fail. All right, section 4, 3 storage strategies. Organizing the factory filing system. So now that we know exactly why we need these precise blueprints, how do we actually go about storing them efficiently? You basically have 3 main choices for version control here. First, there's the ephemeral strategy. This basically means completely ignoring the build folder. Sure, it feels super fast locally, but it completely relies on your CI or other developers to recompile everything exactly right. It's messy, and it highly risks non-reproducible builds. Then you've got the committed strategy. This is where you just commit every single build output directly into your repository. It's incredibly safe, yeah, but it severely bloats your repo size with these massive JSON files. And honestly, nobody wants that in their Git history. Finally, we have the optimal sweet spot, the hybrid with manifest strategy. This is the big one. In fact, if you look at the advanced tracks over at Forge College, they highly recommend mastering this exact approach. You basically keep the source and a tiny lightweight manifest file in your version control, and you only generate the bulky stuff when you absolutely need it. And that brings us to Section 5, building the perfect manifest. This is the ultimate organizational hack, and frankly, it is your absolute magic weapon against all that local environment chaos. So what exactly is this manifest we keep talking about? Think of it as a really compact, version-controlled JSON ledger. Instead of storing the entire heavy blueprint, you're just storing a simple index card. It directly maps your fully qualified contract names right to their exact artifact paths, their ABIs, and their unique bytecode hashes. It permanently pins the identities of your artifacts, but it does it without forcing you to commit thousands and thousands of lines of bulky JSON code into your repository. Let's take a peek at the anatomy of one of these manifest entries. By the way, you can easily generate this yourself using a simple Node script. The script just scans your Hardhat build folder and pulls out only the essentials. It grabs the fully qualified contract name. It records the ABI path, which is just the relative path to where the ABI lives. It calculates a bytecode hash, usually a KKChack256 checksum, just to guarantee that the bytecode hasn't been tampered with. It logs the exact compiler version that was used. And finally, it maps the source metadata. It is incredibly precise and just wonderfully lightweight. And here is how that all flows together in a continuous pipeline. Step 1, you edit and compile your smart contract locally. Step 2, your custom script automatically scans those newly generated artifacts and writes them straight into a nice, clean build/manifest.json file. Step 3, your CI pipeline and your local test harnesses, they just read that manifest. They use it to instantly locate the exact ABIs they need to construct contract factories, verify fingerprints, and run deployment helpers. It is perfectly seamless. I really want you to consider this core takeaway from our source material. The manifest is the low-friction contract between developers, CI, and deployment scripts. Honestly, just building this simple organizational habit is going to save you from endless hours of debugging mismatched builds. It allows your tests to load predictably, and it lets your deployment pipelines reference verified artifacts without ever having to guess or scan through ambiguous, messy directories. We're going to be heading into the Hardhat testing environment in our next module, where this clean manifest is absolutely going to be your best friend. But before we wrap up today, I want to leave you with this thought. In Web3, we are building systems that are designed to be trustless, immutable, and financially binding, right? So if we can't even trust that the code we compiled on our laptop is the exact same code being deployed to the blockchain, how on earth can we ask users to trust the contract itself? Reproducibility isn't just a nice convenience, it is literally the foundation of Web3 security. So to dive deeper into this subject, grab the manifest generator script and explore a huge wealth of other Web3 topics. Be sure to head over and visit forge.college. Thanks so much for joining me on this explainer. Keep those compiler settings pinned, and I will see you next time.